Hi, my name is Juan Suarez, and this is Physics 1, Video Lab 4. In this lab, we delve into the dynamics of a spring mass system oscillating in 2 dimensions. Our aim is to analyze the motion of the mass using both video analysis and computational modeling. By comparing observed motion with predictions and examining energy changes within the system, we seek to validate fundamental principles of physics and energy. In a spring mass system, the second law of motion will always be present due to the force of gravity and its relation to velocity formulas when we talk about kinetic energy and potential energy, which will be mentioned further. The energy principle, also known as the principle of conservation of energy, states that the total energy of an isolated system remains constant over time. This principle is based on the fundamental idea that energy cannot be created or destroyed, but only transformed and transferred. Free body diagrams are visual representations used in physics to illustrate and analyze the forces acting on an object. In a free body diagram, the object of interest is presented as a point particle, and only the external forces are vectors in the equation and picture. Some previews that we may ask are the difference between experimental and the computational data, the relationship between the energies, how the graphs look, and does the coding give evidence to the experiment. The experimental data will be done using a tracker device, and the computational data will be used using a Python script given by our starter code. The relationship between the energy is, as stated before, a conservation of energy. Therefore, the total energy will always be the same, and when some type of potential energy goes up, kinetic energy goes down, and it interchanges like that. A graph will look almost like a sine and cosine graph, where it starts going down and then up because of its change in energy. And then the coding does give evidence to this experiment because it lines up both with our experiment and the code. The system of this experiment is a spring mass system, and the surroundings include air resistance, gravity, external factors, and friction. Some initial conditions that we will have in this lab is the mass of the ball to be 0.402. We have delta T, which is simply the amount of frames we are doing it at, which is 0.095, the gravitational constant, the spring constant, and the relaxed length of the spring. The materials needed are the spring, the mass, a ruler, and a tracker/a recording device. The steps for this experiment are as follows. There's 2 ways to do this, but in our method, we will do the video analysis only, which means we will obtain a video file linked to us. We will use the tracker software to analyze the motion of the mass by extracting the X and Y positions. Then we're going to copy that into a spreadsheet, and we're going to save that spreadsheet into a CSV format to then paste into our computational starter code, where we will get graphs as some results. When we insert the video in the tracker app, we can start tracking the mass by using the auto track feature, and you're going to realize it starts going in a circular up-down motion, which is how we get our X and Y's, which look like a sine and cosine graph where it goes up and it goes down. We're expected to extract the X and Y positions and then take them to an Excel file to then input to our code. When we write the code, we are expected to figure out a lot of different details, including at the top where we have the length of L when it is relaxed. We also can calculate the system energies in the second line, and then we put in a time frame, which would be time is less than 7, where we define our initial energies. We find the force of gravity, the spring force, the net force, and we use the momentum principle as well to find L hat. We use it to find K, delta UG, and a lot of the energies after. And once we do this, we do a loop and we find a graph that will be presented next. Once we click run, we insert the file that we were asked to save earlier in the lab, and we will get these graph results. The bottom left is a computational representation of the video, which is the spring going in a almost circular motion. At the top, we see the changes in energy in delta K, U grav, U spring, and the total energy. And we also have the experimental and the model positions of X and Y, and we can see how they are almost identical with very minor differences. Some sources of error that became present in this lab include the calibration accuracy, the simplification of formulas, and an experimental setup, with the calibration accuracy not being specifically to its measurements, and some formulas being more simplified, and the experimental setup could be more accurate to display a better conservation of energy. For your model, is the energy principle satisfied? Yes. When observing the plot of energy changes, we observe that the total energy remains constant over time, and any fluctuations in individual energy are compensated by corresponding changes in energy forms. For example, how delta spring and delta U coexist with each other, and that delta K is also in there, but delta E, which is the orange line, is always constant. Using the data you obtain in the tracker, make 2 separate estimates of oscillation periods. First, estimating the period of oscillation from the X position and the Y position. So we will take where each graph basically passes their own position. So let's say from 0 to about 1.2, from 3 to about 4.8. We can even make an estimate just off that, but we use the formula on the left, which is a spring constant equals the mass divided by the oscillation time over 2 pi to the power of 2, which is the observed difference between the x and y position is 0.157, and these discrepancies are impacted by calculations, as we mentioned earlier, from the spring constant, the spring force, and the spring potential energy, and other factors such as drag forces, inaccuracies, and camera distortions can affect this accuracy. In this lab, we learned about the dynamics of two-dimensional spring systems in oscillation, and we both learned how to compute and observe this motion and confirm basic physics concepts such as energy conservation, and a clear knowledge of interaction between all types of energy were obtained.